Okay, so last time we had started to look at this chapter on infinite products and Ticular Theorem, and we've begun by doing a little bit of revision of finite products. So we started by looking at the product of two topological spaces, and we saw that what you did was you took all possible products of open sets, one from each space, to give you a certain collection of subsets of the product space x cross y, and these were the basic open sets, and that wasn't yet the topology. You had to say that this was the base for the topology you wanted, so you allow all possible unions of those, and that's what gives you the topology on the product. Then we had our coordinate projections, and assuming x and y are non-empty, we had these surjective coordinate projections mapping the product onto the coordinates separately, and we want those to be continuous. And then the product topology was the weakest, also called coarsest. Topology. This is the one with as few open sets as possible. Obviously, you can make everything open. If you make everything open, then you're guaranteed that the functions will be continuous, but this is not very interesting. So the idea here is to take as few open sets as possible in order to guarantee that the coordinate projections are continuous. And we were just talking last time about the fact that what this means is that you can look at all the preimages of open sets in the first space x using the first coordinate projection. They have to be open. You can look at all the preimages of open sets in the second topological space y using the second coordinate projection, and these sets have to be open. And as long as you ensure that all of those sets are open, that will ensure that your coordinate projections are continuous, and conversely, if they're continuous, those things have to be open. So if you're looking for the weakest possible topology making those coordinate projections continuous, this should be your subbase. And then what you do is you say they have to be open, finite intersections of open sets have to be open, so you have to allow intersecting finitely many of these together, some from each, and then arbitrary unions of open sets have to be open, so you allow arbitrary unions of intersections of finitely many of these, and that gives you your topology on the product space. Any questions about the product topology on a product of two topological spaces? If not, I shall leave you to revise that. Any details that you can't quite remember in full. Okay, so if you've got both of them on the real line with the usual topology on the real line, then when you do the product, it's not obvious. It's a little proof that the product topology gives you the usual topology on R squared. And remember, it's not just products of open sets, because they'll be sort of open rectangle type things. It's unions of products of open sets, and unions of, and that's what you get here. And for example, open disks are indeed unions of suitable open rectangles, if you're careful about the choice of the rectangles. But you need to take a union of infinitely many, of course, to get rid of the spikes. Then you can do the same for finitely many spaces. You can either do that by taking a product of two and then take the product of that with the third, and then the product of that with the fourth, and so on, and that will give you finite products that way. Or you can do it all in one go and just say these are n-tuples, so these are like a bit like vectors with n coordinates, except that there's no addition or anything. It's just that the first coordinate is an x1, the second coordinate is an x2, and so on, and the last coordinate is an xn. So this is equal to x1 up to xn, such that xi is in capital Xi for 1 small equal to I small equal to n. Meaning that has to hold for all I between 1 and n inclusive. So yes, you can do things two at a time, or you can just go back to the coordinate projections and say it's the weakest topology, making all the coordinate projections continuous, in which case you end up with a sub-base just like before. You look at all the open sets in X1 and all the pre-images with the first coordinate projection, and that gives you some sets that have to be open. And then you look at all the open sets in X2 and look at the pre-images of those with the second coordinate projection, and they have to be open, and so on. You do that for each space and each coordinate projection, and that gives you n collections of sets, one from each coordinate, which you know have to be open. And then you have to allow finite intersections of those, and then take products of, take unions of those. And what it boils down to, of course, is in this particular case, you can still get away with looking at products of open sets, one from each set, and that will give you a base for the topology. So that still works for a finite product, but it goes wrong for infinite products, as we'll see. Again, for R to the n, you can think of that as a product of n copies of R, and then you're dealing with the usual topology is the same as the product topology. And again, it's not obvious, and again, it's a little proof. It's much more generally true. It works for metric spaces as well. Let's have a look at what could happen there. Yes. Here's some so-called universal properties. Suppose you want to know whether a map from some topological space into your product is continuous or not. Well, it turns out that if you're not sure yet, all you have to do is check it coordinate by coordinate, which means that you can look at the x coordinates of f of z, and you can look at the y coordinates of f of z, and that will give you two different functions, one into x and another one into y, and you can ask, are both of those functions continuous? If f is to be continuous, then since the coordinate projections are continuous, the composites ought to be continuous. Well, the nice thing is that with product spaces, the converse holds as well. And it all comes back down to this weakest possible topology. So in fact, f is continuous if and only if both of these composites are continuous. One way is obvious, the other way needs a little bit of work. If you don't remember how that works, it's something that's worth checking. Now, suppose you've got two metric spaces, and you take the product space. Well, if you remember, when we've got a metric space and we take a subspace, a subset, we can put the subspace topology on it or the subspace metric on it, and they give the same thing. And that's not obvious, and it needs a little proof. Well, the same thing goes with a product of two metric spaces. If you take a product of two metric spaces, there are various different sensible metrics you can put on it. If you put one of the sensible metrics on the product, then you end up with something that gives you the right topology again, the product topology. Here's some examples. You can just add the two distances up between the coordinates. So you've got xy in x cross y and another point x prime y prime in x cross y. You want to say, what's the new distance going to be? Well, add the distance between the x coordinates to the distance between the y coordinates, and that will give you a nice thing that works as a metric on the product. And if you do that, you can ask, do you get the right topology? And the answer is yes. And the topology you get is the one of coordinate-wise convergence, a sequence xn, yn tends to xy if and only if xn tends to x and yn tends to y. There are some irritating little technical details when you're proving that they give the same topology, and that's going to be on one of the question sheets. But you'd hope that works, and it does. Most of the time, when you think things are bound to work, they do. Every now and then, when you think things are bound to work, they don't. But that's the exception. Okay, that's what I just said about coordinate-wise convergence. So, properties preserved by products. If x and y are Hausdorff, so is x cross y. If x and y are both non-empty, then so is x cross y. if x and y are connected, then so is x cross y, and if x and y are compact, then so is x cross y. Works for locally compact as well, but only because it's a finite product. Infinite products mess up local compactness. So now we want to make a jump and start taking products of infinitely many spaces, maybe even uncountably many spaces, and that will this will come in quite a lot in the functional analysis later, especially when we look at topologies on the dual space, the weak star topology, and later when we come back and look at Banach algebras, when this will be very important when we need the Banach, something called the Banach-Aleoglu theorem about the unit ball of the dual of a norm of a Banach space being weak star compact. So this stuff about infinite products is actually really important and is at the root of the theory of, it's pretty much at the base of the theory of the commutative Banach algebras theory that we'll do at the end of the module. So what have we got? What's our setting? A non-empty indexing set I. It's just a set. But it's a set that we're going to be using to index and say we've got a lot of topological spaces. It could be a finite set. It won't usually be the empty set. I say non-empty to avoid that triviality. I don't want to take a product of no topological spaces because I don't think that makes sense. So there'll be at least one topological space to take a product of, but there might be one. A product of one space is not very interesting. It's basically the same space again. Could be a product, it could be two, then it's back to the usual product. It could be finite set, in which case it will be like the finite products we've just been looking at. Or it could be an infinite set, and it could be uncountably infinite, it could be very big. Quite common for the indexing set to be something like all the elements of a vector space. That will turn up later. So it could well be that it's all the elements of some particular vector space. So I might in fact be a vector space, but and then we take this product over all elements of I, of some topological spaces. So we want to define what does it mean to take the product over I in the indexing set capital I of all the topological spaces xi, and what are we going to use for our product topology? First, we're going to need to get some notation standardized. So here's where the axiom of choice comes in. Now you may not be used to having little x being a function, but it is. I'm going to use a more natural notation in a minute. But here we are. What is going on here? We take the product of all the sets, and the idea is that to have an element in this product, the element will have coordinates, one coordinate for each element in the indexing set. So in a moment, we're going to be saying you've got an element x with coordinates x sub I. The x sub I will be the coordinates of your point of the product. Each xi has to be in the space big xi. But the problem is, because this doesn't have to be a sequence, we actually don't have, we don't know that makes sense. So then you think, what does a sequence mean? Well, a sequence is a function from the natural numbers to a set. So that's what a sequence is. A sequence is really a function from the natural numbers to a set, and the nth element of the sequence is then sort of f of n or whatever. So we generalize that in the natural way, and we say if we want a sort of generalization of a sequence, we're still going to use a function. We have to say where the function takes its values. Well, we want each xi to be in the set capital Xi. So as long as we say that our function is taking values in the union of all the x's, that'll be a big enough set to work with. So you say, let's take the union of all the x's, and that gives us a big set which includes everything we might want one of our coordinates to be. And then we look at all the functions x from I to there, and the idea is that x of I is going to be the ith coordinate. And we're going to call it x sub I in a moment anyway. But just for the moment, so that you know what it really is, Here it is. It's a function that's taking value in the union with the property that for every I in the indexing set, x of I should be in the ith space. Once you've done that and you've got a formal definition like that, then you say, all right, we'll usually write x sub I instead and think of it as the ith coordinate. But remember, we've no idea what this indexing set I is. I could be the real numbers, in which case there'll be a sort of x sub t for every t in the reals. We'll look at that situation in a moment. I could be a vector space, which is what's going to happen later. So there's going to be one space for every element of your vector space. That's quite a big thing. So for example, you could have I could be the open interval naught infinity. Xi could be from, well, I is going to be a positive real number here, so xi can be the interval from minus I up to I, and then we get the product over I and I of xi is just the product of over, I'll change it to t because I'm allowed to change my variable if I want, of the closed interval from minus t up to t. Let's make this a bit bigger. Where was I? Right, so I've got that a bit bigger. And I'm going to take the product of some closed intervals from minus tt. So that's a very big product. It's uncountably many closed intervals. Tychonoff theorem is going to tell us that a product of compact spaces is compact. So this will be a compact topological space when we've understood what the product is. But for the moment, this would be the set of all functions from the positive real numbers to the union of these things. What's the union of those closed intervals? What happens if you take the union of all those closed intervals from minus t up to t? What do you get? You get the whole real line, right? So in this case, the coordinates are taking real values. Surprise, surprise. Of course, in fact, you have to insist that the teeth coordinate is between minus t and t. So its functions from the positive real line to the real line, so that, if you like, the teeth coordinate lies between minus t and t. And you can figure that in terms of functions. You can actually draw a sort of little sketch of what the function does. The function values must lie between minus t and t, so you can actually sort of sketch this. Let's make myself some space and say something about that. So let's have another look at that example. Product from t over t in the positive real lines of minus tt is, so it's those functions f from positive real line goes to r such that f of t is in minus tt for all t in naught infinity, and now you can sketch what a function that's in there looks like. the function's got to lie between y equals x and y equals minus x. So this is, let's call this t, there's y, this is y equals t, this is y equals minus t. And a typical thing in here has to be f. You can use f or you can use x, it doesn't really matter. So if you're using f instead of x, the teeth coordinate of f is f of t. So this shows you the connection between functions and products and coordinates and so on. Any questions about functions, product spaces, points, coordinates? Does that make sense so far, or anything I can explain a bit more? Okay? Right, let's go back to the printed slides. So you've got coordinate projections again. And of course, the idea is that they should pick out a particular coordinate. Now, you get one coordinate projection for everything in the indexing set, just as before with finite products, same for infinite products. You take any particular j in your indexing set and you say pj of your point in the product is the jth coordinate. Well, pj of x, the jth coordinate, I've got two notations for that now. Regarding it as a function, it's x of j. Regarding it as something with coordinates, it's x sub j. That's with the same notation as above. And now, what is the product topology going to be? Also known as the weak topology. Again, you want all the coordinate projections to be continuous, and you want to have as few open sets as possible, so that you'll get that universal property that we had before, where to check the continuity of something that goes into the product, you just have to check all the composites, and then you're okay. So there is now a difference. It turns out that you can't just take one open set from each space and take the product of them all. Oh, I forgot to say, when I mentioned the axiom of choice before, remember, if any of these spaces are empty, it's obvious that the product is empty, because you can't get that coordinate right. If all of the spaces involved are non-empty, then the fact that there is an element in the product is the same as saying that there's a choice function that will pick out an element from each set. So the fact that there's anything interesting in this product at all is the axiom of choice, and tells you that. So now, we're not allowed to just take any old open set from each xi and take the product of them all. And of course you can, in general you can do that. You could just take a subset from each space and take the product, and you'll get a subset of the product, and that does work. It's like saying restricting coordinates and saying the ith coordinate must be in this subset, and so on. But that doesn't give the right topology for our purposes. You get something called the box topology. You get too many open sets. No, it turns out that we have to be a bit more restrictive on which sets are going to be open. So let's have a look at what's going on here. So moving past that slide, here we are. So don't forget to check that you do get the same figures before if you took just two topological spaces, or finitely many topological spaces. It's also worth thinking about what happens if you take a sequence of topological spaces, because that's an interesting special case. So if you just take the natural numbers, then your indexing set being the natural numbers, so you've got one space for each natural number, and you take a countable product like that. But more generally, we're probably going to be taking uncountable products. So here's your subbase. It's exactly the same as before. You look at every possible coordinate and every possible set which is open. This Tor I is the topology of the ith topological space. So this is a set U that is open in Xi. So you've got a set that's open in Xi. You want the ith coordinate projection to be continuous, so the pre-image should be, we want that to be open in the product. So we look at all the possible things you can get that way, and so of course you've got lots of different coordinates and lots of different open sets, and this is a big collection of sets, but we do know that we want those to be open if we want the coordinate projections to be continuous. And we want the weakest topology making them all continuous. So all you need to do is say, these are the ones we need to be open, generate a topology from that. But you have to generate them by making this as your subbase, because you don't expect this to be a base. And it isn't, usually. So this is your subbase, which means you take finite intersections of those. And then that's a base for your topology. So here's your standard procedure. B is a set of all possible finite intersections of elements from this. Now, you could say, and the empty intersection is the whole thing, but alternatively, you can note that if you take U to be the whole of Xi, then the pre-image of the whole of Xi will give you the whole product anyway. So you've got a choice as to whether you like the intersection of no elements of your subbase or not. And by convention, if you intersect nothing, then you get the whole set. If you intersect no sets, then you get the whole space you're working in. But I don't like that very much, because it doesn't actually make sense. The intersection of the empty set is not in general well defined, because you would need to know which set you were working in. But if you say, we are working the product, then you're okay. Doesn't matter here, because you've got plenty of specific things you can work with. So you look at all the finite intersections, and that gives you a base, and then you've got basic open sets. And what are those basic open sets? They look like this. You take some i's, some indexes, usually different ones. There's not usually much point in taking the same one twice, because you could have intersected the relevant U's already. And then you take a set UK, because I've chosen an IK to be a particular index. So we're working in XIK there. So UK is a set that's open in XIK. Then you look at the pre-image of that under the coordinate projection, and that says those elements of the product where the ikth coordinate is restricted to be in UK. So the ikth coordinate must be in UK for 1 small equal to k small equal to n. In other words, we put a restriction on finitely many of the coordinates, but not on any of the others. So if you want a basic open set, they're actually really usually pretty huge, because you're only allowed to put a restriction on finitely many of the coordinates, and the rest of the coordinates, you have to allow them to be arbitrary. So these basic open sets are really usually quite enormous. So here's the alternative way of thinking about it. Yes, the basic open sets are done by taking products of open sets from the xi's, but almost all of those vi's have got to be the whole space. You're only allowed to put restrictions on finitely many coordinates for your basic open sets. So for all but finitely many i's, you have to allow vi to be xi, and then you put restrictions on some of the others. So this is rather different, except, of course, if you go to the special case of the finite product, if you go to the finite product, they're the same, because all but finitely many means as many as you like if you're working in a finite product. It gets a bit hard to visualize once you're into infinite products. Does anyone have any questions so far on the infinite products, what an element of an infinite product is, or what this topology is? If you use nets, by the way, if you learn about nets, which I don't do in this module, you'll discover that the convergence is coordinate-wise convergence. So you get the right notion of convergence for nets. If you've got a net in the product, then it will converge to a point in the product if and only if each of the coordinate sequences converges to the right coordinate. But I said coordinate sequences, I should have said coordinate nets. Because you have to work with a generalization of sequences, because you may well not be working with anything metric. And even if all of the spaces are metric spaces, if you take an uncountable product, you don't usually get a metric space in the end. The box topology says, why not just allow all possible products of open sets, but you get too many open sets and everything goes wrong, and Tychonoff's theorem will fail and it will be hopeless. So that topology, it is known, it's occasionally used, but it's generally not got very good properties. It doesn't give the right notion of convergent nets, you don't get coordinate-wise convergence, and so on. Everything goes wrong. So we won't use the box topology. So from now on, we're always going to assume that that's what we've got. If we take any old product of topological spaces, we'll always use the product topology on it. If I forget to tell you, that's the topology I mean. There will be exceptions where some things have got more than one topology, especially when we're dealing with certain kinds of vector space, which may have a norm topology and some product topology as well, in a way that I'll explain later. The coordinate projections are continuous, because that's how we define the topology. Here you are, this is what I said about the axiom of choice. The product is non-empty if and only if all of the spaces are non-empty. Assuming that they are all non-empty, and again, we're still using the axiom of choice in all this, then the coordinate projections are surjective. Then some things that are less obvious that you should investigate for yourself if you've never checked this before. Show that these things are open mappings. What's an open mapping? An open mapping is almost the opposite of a continuous function. A continuous function, what's the definition of a continuous function in a topological space?
If f is a function from
yes.
x to y,
Yes.
then f is continuous if the u opens it in y.
Yes.
If inverse of y is open in x.
Yes, that's right. So continuous is that pre-images of open sets must be open. Well, an open map is that images of open sets must be open. Now, that's very different from being continuous, because, for example, consider a constant function from the real line to the real line, like the function that's constantly equal to 1. Well, usually then the image of an open set is not open. In fact, the only open set whose image is open is the empty set in that case. So you can't get much more continuous than a constant map, but that's very much not an open map in that setting. So example, constant maps from R to R are continuous but not open. So they're not open mappings. But the coordinate projections always are. And that's something to think about. But it comes down again to the definition of what's going on and how things work. And you can check that it works on basic open sets. If you take a basic open set, you can immediately see what the coordinate projection does to it. And then you can see what the coordinate projection does to a union of basic open sets. And it works. Here's something that's coming up on a question sheet. So, if they're all metric spaces or metrizable spaces, and you're just taking a sequence of them, then it turns out you can put a metric on the product. So, a countable product of metrizable spaces is metrizable in its product topology, but it's not immediately obvious what the metric you should use is. However, again, you pick out coordinate-wise convergence. So you need some notation for it. But if you take a sequence, it's a problem. You end up with a sequence of sequences, because every element of this product will be a sequence. And you want to take lots of them. So you end up with a sequence of sequences, and then you have to choose your notation. We'll come up with some notation for that in a bit. But let's not worry about that for the moment. But you've got your sequence of sequences. You want to know, does it converge to some other sequence? Well, you just check it coordinate by coordinate and say, do the first terms in the sequences converge to the limit sequence first term, and so on for the second term, for the third term. And so you get coordinate-wise convergence. And this time you can use sequences instead of nets. And there'll be lots of other things to check for you on the question sheets. And that brings us on to the beginning of this section on Tychonoff's theorem. And as I said, the Tychonoff theorem is going to be quite a tough proof. Let me start by reminding you what the finite intersection property is. So you got some sets. It's a slightly curly S. It's a set of subsets of X. So let's just warn you about what's going on here. S is a subset of P of X, which means that S is an element of P of X. I'll do a curly S like that, actually. So here's my handwritten curly S. It's slightly different in the printed notation. So this is S is an element of P of X. What does it mean? So it's got the finite intersection property. Whenever you take finitely many things in S, their intersection to be non-empty. In particular, n equals 1 is possible, so any element of S should be so any of the elements of S must be non-empty themselves, but not just that. If you take any finite number of them, you get a non-empty set. But that doesn't force, in general, the intersection of all of them to be non-empty. Who knows an example of a collection of sets where all the finite intersections are non-empty, but when you intersect them all, you get the empty set? So a concrete setting, like subsets of the natural numbers or subsets of the real numbers. Anybody know something where whenever you intersect finitely many, you are non-empty so far, but by the time you intersect them all, it ends up empty? I suggest taking a nested decreasing sequence of some sort whose intersection overall is empty, but where none of the things are empty. Does anyone know one? If you go from minus 1 over n up to 1 over n, you're just unlucky. Let's have a look at some examples. Did you want open, by the way, or closed? Okay. So the intersection from n over n in the natural numbers of the open interval from minus 1 over n up to 1 over n has got one point in it. Does anyone know how to modify that to get an example where the intersection is empty? 0 up to 1 over n, yes. The intersection over natural numbers of 0 up to 1 over n is empty. So these sets, this collection of sets S equals, or curly S, equals intervals from 0 up to 1 over n, such that n is a natural number, that has FIP, because if you intercept finally many of those, you just get the smallest one so far. And that's non-empty. But if you intercept them all, you get the empty set. So that shows that FIP is an easier property to have. It's easier to have FIP than to have the property that the intersection of the whole lot is non-empty. However, there are certain settings where one implies the other. Well, okay, one already implies the other. If the intersection of them all is non-empty, then every finite intersection of them is non-empty. But the other way around we don't expect to get in general. But it turns out that there's a characterization of compactness in terms of FIP. If you haven't seen this before, it's something to revise from metric and topological space theory. So how do you know if a topological space is compact? It's the following. Suppose you take a non-empty collection of closed subsets, and suppose that they've got the finite intersection property. Then when you intercept them all, you should get something non-empty as well. So this is the reverse implication under special circumstances. If you're working in a compact space and you've got an FIP collection of closed sets, then the intersection of them all will be non-empty. So if you think about it, go look at the example we just had. What was the problem? Well, they were open sets instead of closed sets. You could have said we were working in a sort of compact space between minus 2 and 2. Okay? So you could have said we were working in a compact space between minus 2 and 2, and we had a collection with the finite intersection property, but it had empty intersection. Why? Because we work with open sets instead of closed sets. If you close those sets up, they've all got naught in, and the intersection still has naught in as well. And that's going to be relevant to one of the things we're going to say in a moment. So Tychonoff theorem says every product of compact spaces is compact, even for uncountably many compact spaces. And to prove it, we're going to have to prove some lemmas. And let's slightly generalize what we just said about the FIP setting as well. So this time we don't insist that the sets in S are closed, but we fix it by closing them all, just like the example I was saying. So your space is compact if and only if the following holds. You've got whenever you've got a non-empty collection of sets with the finite intersection property, well, we've already seen by an example that you don't necessarily expect the intersection of the ball to be non-empty. But if you close them all first, the intersection of those closures must be non-empty. And now just think about that without, I'll exercise it to check the details. I'll just say orally what's going on there. If the sets have got the finite intersection property, then their closures also have the finite intersection property. And so the intersection of the closures should be non-empty if it's compact. On the other hand, if you know this holds, and you've got a set of closed sets of the finite intersection property, then it's already one of these sets as well, and the closures don't change anything. So the intersection should be non-empty. So it's actually really easy to get between these two different versions. In one case, you have to do nothing, and in the other case, you take the closures and say it's still got the finite intersection property. So it's actually quite an easy exercise to check that the equivalence of this to the standard FIP thing. Now, what does it mean to be in the closure of a set? You're in the closure of a set if and only if you can't find an open set round you that misses the set. It means that every open neighbourhood of the point must meet the set in a non-trivial way. So what's going on here? For x to be in the closures of everything in S, that's if and only if x is in, if and only if for every A in your collection, x is in the closure of that A, and x is in the closure of A if for every neighbourhood of x, U intersection A is non-empty. So if you combine those two, this is what it means to be in the intersection of the closures. It's for every neighbourhood of U, every neighbourhood of x, and every set in your collection, U intersection A must be non-empty. And so that's what you would want to check if you want to establish that x is in that intersection. And that's what we'll be doing in the middle of the proof of Tychonoff's theorem. And to save time, I'm going to call a non-empty collection of sets which has the finite intersection property. That takes too long to say, so I'm just going to call it an FIP collection. And I'm going to be talking about FIP collections of sets. Not standard, but it does save a lot of time. And we're going to use Zorn's lemma to say that every FIP collection is included inside some maximal FIP collection. And the maximal FIP collections turn out to be something called ultrafilters, which do have another definition as well. And by looking a little bit at the theory of ultrafilters, we'll prove Tychonoff's theorem. And we'll do that tomorrow.